Hello everyone, my name is Valentin Dimitri Popescu, and I'm honored to present an end-to-end TinyML vibration sensing node for real-time event classification on STM32L4. The system combines a high-resolution accelerometer, a quantized 1D ResCNN, SD card logging, and secure LoRaWAN communication in a battery-powered embedded platform. I will briefly cover the motivation, the research gap, the system architecture, the implementation workflow, the main results, and the final conclusions. I will start with the motivation behind this work. The main motivation is to move vibration analysis from the cloud to the edge. This reduces latency, saves bandwidth, improves privacy, and supports long-term remote deployment through ultra-low power operation. This type of system is relevant for intrusion detection, industrial monitoring, and structural health monitoring, where it is important to capture subtle vibration events and make decisions locally without continuously transmitting raw data. Next, I will briefly position this work relative to existing literature. Existing work usually address only part of the problem, either vibration classification or embedded sensing or compact neural models. What is still missing is a complete deployable node that combines accurate on-device classification, low power operation, secure model updates, and efficient decision level wireless reporting. Um, in this context, 1D residual CNN are a strong choice for time series classification because they extract temporal patterns efficiently while remaining stable during training. ADQIT is also important because it reduces model size and inference cost while preserving classification performance. The research gap is the lack of an integrated TinyML solution that combines quantized ResCNN on STM32L4, secure over-the-air model updates, decision-only LoRaWAN uplinks, and SD logging of raw signals for retraining and traceability. The problem is that vibration monitoring is very useful in security, industrial, and structural application, but difficult to implement on a battery-powered embedded node. The challenge is to achieve reliable real-time classification under strict constraints in memory, energy, and communication, while also keeping the system maintainable after deployment. This leads to four main questions. Can a fully quantized 1D ResCNN run accurately on STM32L4 in real time? Can quantization reduce memory and computation enough for deployment? Can an event-driven sensing and inference pipeline provide long-term autonomy? And can the complete system supports secure over-the-air updates, decision-only LoRaWAN reporting, and SD-based traceability? I will now present the proposed system and how it is implemented. The system is built around four main elements. The STM32L4 microcontroller for control and inference, the ADXL355 accelerometer for high-resolution vibration sensing, the LoRaWAN radio for communication, and the micro SD card for local storage and model management. At runtime, the firmware follows an event-driven workflow. The STM32 stays in shutdown mode most of the time. When the ADXL355 detects motion, it generates an interrupt and wakes up the microcontroller. The MCU then starts real-time acquisition into 4 kilobytes RAM buffer, performs window on device inference, stores the event on the SD card, transmits only the final decision, saves metadata, and then returns to shutdown. This sequence is central to both energy efficiency and system robustness. A key implementation decision was to use a circular log file on the SD card. This avoids the repeated file open and close operations, reduces fragmentation, and supports fast sequential writes during real-time logging. Each recorded event is stored as a self-describing binary record with 3 fields: 4-byte event index, 4-byte sample count, and the raw accelerometer samples, where each sample contains X, Y, and Z values stored on 6 bytes per sample. When storage becomes full, the oldest events are overwritten automatically. This makes the logging scheme simple, efficient, and suitable for later dataset extraction. For signal preparation, the ADXL 355 samples the 3-axis vibration signal at 96 Hz using its internal low-pass anti-alias filter. The incoming stream is segmented into fixed windows of 192 samples for each of the 3 axes. If the detected event is shorter than the required length, zero padding is applied to preserve a fixed input shape. Then each axis is standardized using z-score normalization based on the training set, mean, and the standard deviation. This ensures that the model receives consistent inputs and improves inference stability on the embedded device. The proposed model is a compact 1D residual CNN designed for vibration signals. It takes as input a normalized window of 3-axis accelerometer data and process it along the time dimension. The first part is the feature extraction stage, where 1D convolution learns short-term temporal patterns from the vibration signal. Residual shortcuts help preserve information flow and improve training stability. Next, the compact representation stage progressively reduce the temporal dimension while retaining the most informative features. This is important because the model must remain both discriminative and efficient enough for embedded deployment. Finally, the classification stage maps the extracted features to the probabilities of the 4 vibration classes. Overall, the key idea is to use residual learning to improve feature extraction while keeping the architecture compact enough for quantization and execution on STM32L4. I will now move to main experimental results. The model achieves strong classification performance, reaching 97.7 accuracy on the clean test set. The confusion metric shows the strong class separation, and remaining errors mainly appear between structurally similar vibration classes. This result shows that a fully quantized ResCNN can still provide reliable real-time vibration classification on a resource-constrained embedded platform. The second key result is robustness to noise. Performance improves as the signal-to-noise ratio increases, which is the expected behavior, but the proposed model remains comparatively stable under moderate noise. This is important because real-world vibration signals collected in the field are not perfectly clean. so robustness is necessary for practical deployment. At system level, the most important result is a battery life. The node stays in shutdown mode for more than 99% of the time, where the total current is only about 21 microamps. When an event is detected, the sensing and the machine learning part becomes active for a short time at about 820 microamps for around zero 0.5 seconds. Then LoRa transmission uses the highest current, about 20 milliamps, but only for around 0.9 seconds. So even if the radio is the most power hungry part, it is active only very briefly. With a 1200 milliamps hour battery, this low standby current corresponds to an ideal lifetime of about 6.5 years. If the node remains mostly idle, in real operation, the lifetime is lower because the system periodically wakes up to acquire data, run inference, and transmit results. However, since these active phases are short, the expected battery life is still remains in the multi-year range for realistic event rates. Compared with simpler baselines, the proposed model offers better overall accuracy and stronger robustness under noise, while also remaining feasible for embedded deployment. This means that the contribution is not only better classification performance, but also a better practical trade-off between accuracy, latency, memory usage, and system level deployability. I will finish with the main conclusions. In conclusion, this work demonstrates that complete TinyML vibration sensing node is feasible on STM32L4. The final system combines high fidelity sensing, quantized ResCNN inference, SD-based logging, and LoRaWAN reporting in a coherent embedded workflow. The main contributions are the event-driven low-power system architecture, the compact quantized ResCNN pipeline, and the secure and traceable integration of local storage with wireless reporting. Future work includes extending the system beyond the four classes, validating it in more diverse real-world environments, and further improving scalability without sacrificing autonomy or security. These are the main references. Thank you for your attention.